Examples on one-dimensional wave equation. A tightly stretched string with fixed endpoints x equal to 0 and x equal to L is initially in a position given by y of x comma 0, which is equal to y naught sine cube pi x by L. This is the position of the string. If it is released from rest from this position, find the displacement y at any point and at any distance from the end x equal to 0. So we have to find what is the displacement y. Step 1. So for the entire unit, we are going to write the solution in this format, in this steps only. Step 1, step 2, step 3. It is similar for all the examples, only the boundary conditions and initial conditions varies. So step 1, we have to write what is the governing equation of transverse vibration of a elastic string. So the displacement y of x comma t is governed by this equation is one-dimensional wave equation. Dou squared y by dou t square, which is equal to a square dou squared y by dou x square. Remember, left hand side with respect to t, right hand side with respect to x, which has coefficient a square, where a square is equal to t by m. So step 2, we should write the boundary conditions. So there are two boundary conditions and two initial conditions. All together in few books they will list this as boundary conditions itself. So first two conditions are boundary condition. It is based upon the boundary end point of the string. So this end is x equal to 0, the other end is x is equal to L. So what is y when x equal to 0 in this end? The end points always will not have any displacement. So usually at the end the displacement is 0. So y is equal to 0 when x is equal to 0. Retain this t as it is. Then second boundary condition is when x equal to L, another boundary is x equal to L. Here also there is no displacement. So y is 0, displacement is 0 when x is equal to L. So existing variable is t and we have tried the range for t. So for all t greater than or equal to 0. These two conditions are called as boundary conditions. Here we are discussing for x equal to 0 and x equal to L. The next two conditions are called as initial conditions. So here we are going to substitute t as 0 and we will write what is y. So t is equal to 0, what is the displacement? It is given in the problem. When t equal to 0, y is given as y naught sine cube pi x by L. So it is y naught sine cube pi x by L. For existing variable is x here and the limits for x varies from 0 to L because the length of the string is L. So x varies from 0 to L. And the other condition is dou y by dou t at t equal to 0 equal to 0. From where we are getting this condition means it is given in the problem. It is released from rest from this position. So initially the string is in this position and it is released from rest in this position. I have given a note already. If it is given initially it is released from rest, you should take this condition as one initial condition. When time t equal to 0, the velocity dou y by dou t is equal to 0. So that is the last condition, dou y by dou t at time t equal to 0 equal to 0. And we should write the range of x as it is what we did in the previous condition. So these are the four conditions. So for first two is for x equal to 0 and x equal to L boundaries. Other two conditions at time t equal to 0, what is displacement and what is velocity. Next step 3, we have to write what is the solution of one-dimensional wave equation which governs the vibration of transverse vibration of an elastic string. So the solution just now I explained in the previous lecture that the proper solution for the physical nature of this problem is this. So you have to take the solution as it is: a cos lambda x plus b sin lambda x into c cos lambda at and d sin lambda at, where a, b, c, d are arbitrary constants. So our aim is to find what are the values of a, b, c and d using the condition listed here. So I have this is equation number 2. Now we are going to apply first boundary condition in equation 2. So what is the first boundary condition? It is y of 0 comma t is equal to 0. So when x is 0, y is 0. So if I substitute x as 0 and y is 0 means left hand side is 0. X is 0 means cos 0 is 1, sin 0 is 0. This term will go off. So you will have only a here. These two terms you have to retain as it is. So you will get a into c cos lambda at plus d sin lambda at and you can equate a to 0. So using boundary condition 1, we get a equal to 0. Then next is boundary condition 2. So boundary condition 2 is we have to substitute x is equal to L and y is 0. When x is equal to L, y is 0. This we have to substitute in this solution, second equation. So y is 0, left hand side is 0, right hand side a is already 0, no need to write this. And here x we have to substitute it as L. These two terms we have to retain as it is. So we get b sin lambda L, c cos lambda at, d sin lambda at, you have to retain as it is. And now we cannot able to equate b to 0 because already a is 0. If we equate b to 0, the entire solution will become 0, which is meaningless. So therefore we can equate only sin lambda L to 0. So if b is 0, solution becomes y equal to 0, which is not true. So therefore equating sin lambda L equal to 0, lambda L is equal to sin inverse of 0. What is sin inverse of 0? At what angle sin will takes the value 0? At the value at angle n pi, where n varies from 0, 1, 2, 3, etc. When n is 0, the angle 0, sin will take the value 0, angle plus or minus pi, plus or minus 2 pi, everything sin will take the value 0. So in general we are writing it as n pi. Sin inverse of 0 is n pi. So therefore lambda is equal to n pi by L. So substitute now these two conditions, these two values, a equal to 0 and lambda equal to n pi by L in equation number 2. That is in this solution. Substitute a value and lambda value and rewrite this solution and have it as equation number 3. Now we should use the fourth condition. Why I am not using the third condition means, first our aim is to use all the 0 boundary conditions, means right hand side whichever conditions are 0, have to write that, use that first, and then I should generalize the solution. At last only I should use the non-zero boundary condition. It is a rule. So now I am going to use the fourth condition. For that I need the derivative, partial derivative of y with respect to t. So the third equation I am differentiating partially with respect to t. So if I differentiate third equation partially with respect to t, the other variable I should retain it constant, x is constant. So retain this term as it is. Only I should differentiate the function t. So if I differentiate cos, I will get minus sin n pi at by L, and if I differentiate this n pi at by L with respect to t, I will get into n pi a by L. Similarly, if I differentiate sin, I will get cos n pi at by L into, if I differentiate n pi at by L with respect to t, I will get n pi a by L. So now I have to apply the fourth condition. Fourth condition is dou y by dou t at time t equal to 0 is 0. So this velocity is 0 at time t is 0. So if I substitute t as 0 in this, sin 0 will become 0. This term will go off, and cos 0 is 1. So you will get d n pi a by L. That is what I have written here. This term b sin n pi x by L I have to retain as it is. Now we cannot able to equate b to 0 because already a is 0. So the only option is we can equate d equal to 0. So using initial condition fourth, otherwise I can call it as boundary condition also, we are getting d equal to 0. Now substitute this d equal to 0 in this updated solution in equation number 3 and rewrite it. So if I substitute, I will get d is 0 means only the c cos n pi at by L will exist. So now b, c both are constants, I can combine together and I can write it as bn, remaining terms as it is, sin n pi x by L, cos n pi at by L. So now I am going to write the general solution, which is called as most general solution, satisfying equation 1 is one dimensional wave equation, and the boundary conditions 1, 2, and 4 is just most general solution, means it is nothing but in this solution put one summation. Summation n varies from 1 to infinity and write these terms as it is. This is called as most general solution, equation number 4. This is very important step, it carries few marks. Then after writing this most general solution, then only we should use the non-zero boundary condition. That condition is the third condition. This condition we should use. So what this condition says here is, at t equal to 0, at time t equal to 0, y, the displacement is y naught sin cube pi x by L. So I have to substitute this in fourth equation. So I have to substitute in fourth equation this y as y naught sin cube pi x by L, and in the right hand side t equal to 0. So t equal to 0 means I will get cos 0 is 1. So remaining I'll get it as summation bn sin n by x by L. So now I got one function of x in the left hand side. Right hand side it is summation bn sin n by x by L. So the right hand side is nothing but off range, Fourier off range sine series. So if it is Fourier off range sine series, I know what is the formula to find what is bn, taking the left hand side function as f of x. Using that I can find what is the value of bn, and that bn I can substitute in equation number 4. That is the usual way of finding bn. But in this problem we are having sin cube pi x by L, which is of the form sin cube theta. Instead of going for finding bn comparing with the Fourier off range series, we can directly find what are the values of bn by expanding this sin cube theta with the trigonometric formula. The trigonometric formula for sin cube theta is 3 sin theta minus sin 3 theta by 4. So in the place of theta you are having pi x by L. So I can rewrite the sin cube pi x by L as this y naught is constant, even as it is. So I can rewrite it as 3 sin theta. So 3 sin pi x by L minus sin 3 theta. Theta is pi x by L, 3 pi x by L divided by 4 I am writing here. And right hand side if I expand, I will get b1 sin n pi x by L, b2 sin 2 pi x by L, b3 sin 3 pi x by L, etc. Substituting n as 1, 2, 3. So you will get terms like this. And the left hand side if I rewrite, I will get the first term as 3 y naught by 4 sin pi x by L. Second term is minus y naught by 4 sin 3 pi x by L. So apart from these two terms, no other terms are available in the left hand side. That is what I am writing here in the right hand side. So now I am going to equate the like terms. So here sin pi x by L is there in the right hand side. Here also in the left hand side sin pi x by L is there, whose coefficient is bn. Here the coefficient is 3 y naught by 4. So equating the like terms coefficient, I will get b1 is equal to 3 y naught by 4. So the sin 2 pi x by L term is not available in the right hand side. So b2 is equal to 0. Then sin 3 pi x by L is available here and also in the right hand side. The coefficient is minus y naught by 4 and here the coefficient is b3. So b3 is equal to minus y naught by 4. No other terms are available in the right hand side, so I cannot able to compare with the left hand side expansion. So I can assume that all other bn's is 0 except b1 and b3. So bn is equal to 0 for n not equal to 1 and 3. So we got values for b1, b3. I should substitute these two values in the updated general equation, that is equation number 4. So I have to expand this expansion substituting n as 1 and n as 3, because all other bn's are 0, only b1, b3 exist. So therefore I will get the solution as 3 y naught by 4 sin pi x by L cos pi at by L minus y naught by 4 sin 3 pi x by L. This is the value for b3. So sin 3 pi x by L cos 3 pi at by L. So before listening to this, you should get ready with the PDF, so then only it will be clear for you. Whatever I am explaining, whichever is required, you can write the details at the side. Next example, a tightly stretched string. Okay, next example we'll see in the next lecture. Thank you.